All right, we've reached the final step in the definition of our generative adversarial network. We first defined our discriminator. We then defined our generator. We used a few different layer types, a couple of new ones along the way. So we saw deconvolutional layers and upsampling layers for the first time as a part of our generator forging these images. So the deconvolutional layers, these are kind of like the inverse of a convolutional layer. And the upsampling is like the inverse of the max pooling layer. So over the course of the deconvolutional layer, we're taking a random sample from our 100-dimensional latent space, and we're using that noise to start with a 7 by 7 pixel image with quite a bit of different filters, so 64 different filters. And then over the course of the generator, we reduce those number of filters down to one final filter that's 28 by 28. So the number of the filters decreases over the course of the generator, but the size of them decreases from 7 by 7 to 28 by 28 until we're generating a fake image, 28 by 28 pixel with 0 to 1 values representing the darkness of each pixel, and that corresponds precisely to the 28 by 28 pixel images that are coming in that are real as well into the discriminator. Over the course of the discriminator, we do the opposite. We have convolutional layers taking that 28 by 28 pixel image, parsing it, calculating a number of different filters, an exponentially increasing number of different filters as we go deeper into the convolutional layers until at the final layer, this discriminator is able to guess as to whether the 28 by 28 pixel image that goes into it is real or fake. So we have these two pieces separate now. It's actually really easy to tie them together into a single adversary. So going through our code here, we have the discriminator definition. We created an instance of a discriminator. We go through our generator code here. We created an instance of the generator. Now we can tie them together into a single adversarial network. So let's give this a nice little comment here. Create adversarial network. And we're going to define our adversarial builder with the same kind of syntax as we did the discriminator in the generator. The only hyperparameter here is the number of dimensions of our latent space, which we've set to 100. This time we're going to use our classic sequential Keras model. It makes our lives a little easier. We don't need the granularity of the capital M model way of doing things. So with this, we just use the add method on this instance of a model that we create. And we add the generator. So that's where we start with the generator. And then we add the discriminator. That's it. We can compile the model right here with the compile method. We're going to use cross-entropy loss, same as in the discriminator because it's the most efficient kind of loss that we've learned about. Our optimizer, just like in the discriminator, is going to be RMS prop. And we're going to set different hyperparameters to our discriminator. So we're going to have the same ones, learning rate, decay, and clip value. The clip value on our gradient is going to remain 1, just to make sure that our learning rate doesn't, or gradient doesn't get out of control anywhere. And we're going to set our learning rate to 0.0004, which is half of what we had in the discriminator. And we're going to set our decay also to half the rate, so 3 times 10 to the negative 8. So half of the decay that we had in the discriminator. This is an example of the finickiness of generative adversarial networks. A lot of people complain that it's difficult to get them to work, and part of this is getting this specificity of how quickly we're learning with the overall adversary relative to the discriminator on its own. And so we found that these hyperparameters with all of the other network architecture that we set up works well. And as we often do, our metric for observing how our adversarial network is performing over time is going to be accuracy. And we can have this function output a model summary as well. And of course, it's going to return the model because that's why we're building it. So then we can create an instance of an adversarial model by using our adversarial builder. And then we see in the summary that we're starting with our generator. It outputs a 28 by 28 pixel image. Because it's black and white, we only have a dimension 1 here. And then the second part is the discriminator, which outputs a single value representing the probability that the adversarial output is a real or a fake image. There is one funny thing we need to do once we start training this. So let's add a little comment here to say that now we're going to train our adversarial network. But we're going to define this function. This is a special function unlike anything we've done before. We're going to call it make trainable. Make trainable takes in a neural net as a input, as well as a Boolean value representing whether the network should be trainable or not on our command. The reason why we're doing this is we're using the discriminator in two different ways. I mentioned this a little bit earlier, and this will make more sense again as we get into writing the code in a moment. But the discriminator is used twice. It's used once on its own to discriminate real from fake images, and in that instance, we want to be training the weights in the discriminator. Then we're going to freeze those weights with this make trainable function so that as a part of the whole adversarial network, the discriminator's weights aren't changing, we're only changing the weights in the generator. So to make sure that we are affecting all of the layers in that discriminator, we're going to say for layer in net layers, set L trainable equal to true or false. Okay, now we can actually get into the training. So we're going to define this train function. You can set the default number of epochs to whatever you like. I'm going to set them to 2,000. And we're going to set our batch size to 128. So this is the mini batch size for stochastic gradient descent. We're going to have the same batch size for training our discriminator as well for training our whole adversarial network. We're going to create a couple of values to store the performance of both the discriminator and the adversarial network as we're training so that we can observe its performance over time. So we're going to create a list that's starting empty to contain our discriminator metrics as well as our adversarial metrics. And we're also going to track loss, so the running loss that we can observe over time in the discriminator. So it starts as a 0. So here we're watching our loss, our cost function that we're trying to minimize. So we're going to watch our cost function as we train the network in both the generator and the discriminator. So here's the running discriminator loss. And we also have our running discriminator accuracy. So what percentage of images is it correctly classifying as real or fake? We can observe that change over time by tracking this. And we're going to do the same with our adversarial network as well. Cool. So now we actually can get into the code for running an epoch. So for an epoch, within our range of epochs, I like to do a little modulo operation here so that I can make sure that something's happening. I just like to know, and on my machine, every 100 epochs ends up being the kind of right speed for me to be confident. You know, after a few seconds on this box, I get the validation on the screen that some kind of compute is happening. On your machine, that number might be higher or lower, or also based on your attention span, your need for affirmation. So now we're going to, for this individual batch, we're going to sample our real images as well as our fake images. So let's start with the real ones. So the real images, we're going to sample with the NumPy random function. We're going to sample from all of the possible real images in our data set, and we're going to sample a size of batch of 128. So here's our whole sample, in my instance, 150,000 different Apple images. So we're going to pick 128 of those at random to be our real images for this individual batch. And we're going to do that without replacement. Great, so that line of code gives us our real images in the correct shape, a sample batch. Now let's do the same thing with our fake images. To create our fake images, we actually use the generator. So of course in the beginning, these fake images created by the generator are going to be really weak. They're going to be just random noise in the beginning before we've started training our generator. We've got to start somewhere. And so we use the predict method on our generator to create some fake images. We're going to pass in noise on the range of -1 to 1. So this is going to be our random sample from latent space coordinates, and the size of that sample is going to be 100. That's the number of dimensions that we defined above. When we defined our discriminator and our generator, we decided on having that 100-dimensional latent space. And we're going to sample 128 of those per batch, so we have the same number of real and fake images per batch, 128 of them. The next step is to concatenate the real and the fake images together into our inputs for the discriminator network. So we just use the concatenate operation to add the real and the fake images together as our inputs, and now we need to label those inputs as real and fake respectively. So we can do that by creating a y variable that has twice the size of our batch, and it starts as all ones, but then we say we want the first half of them to be labeled differently from the second half. So that'll do the trick there. So now we have our x's, our real and our fake inputs for the discriminator, and we have our labels for the discriminator as well. We're going to use that make trainable function that we just defined on the discriminator, and we're going to set the discriminator to be trainable here. So all of the weights can be trained by running this line of code, and then we can train it. So we append to our discriminator metrics list the results of training on a batch with the x and y values that we just defined. And we're also going to keep track of our running discriminator loss and our running discriminator accuracy here as we go along so we can keep an eye on things, make sure that everything's happening as we expect. So it's simply the last value here. We're saying the -1 means I'm taking the last value from my d-metrics list. And the 0 corresponds to loss. So this train on batch method for our x and y batch is outputting two things. It outputs the loss and it outputs the accuracy onto this d-metrics list. And then here we take that last entry that was just added and add that to our running metrics. Now, so that's how we train the discriminator. That's it. We trained it with those few lines of code. But now we want to train the whole adversarial network. To do that, we want to freeze our discriminator weights so that they can't change. So we set our discriminator trainable to false. We sample some random noise again. And this has the same parameters as last time. So we can grab this line of code, paste it here. So again, we're sampling 128 random values from our 100-dimensional latent space as an input to our adversarial network now. And in this case, we label all of them as real, even though they are fake. So for the discriminator, we're giving it 50-50 real and fake images, allowing it to train on those correct labels. We freeze the weights in the discriminator, and then we train the whole adversarial network, allowing only the generator weights to move around, where we're feeding in fake images, but labeling them as real, so that the difference between fake and real, that cost, is decreased over time. Our cross-entropy cost is decreased, and so the generator becomes better and better at creating fake images that look like real ones. So in the same way that we appended metrics for our discriminator, we're also going to append metrics to our adversarial network as we train. So here our adversarial model is going to train on batch. The inputs into the adversarial network are just noise. So we change X to noise. And then our running adversarial loss and accuracy are also tracked. So that's kind of the main part. The last thing that we want to do so that we can watch our adversarial network train over time, all of the steps that we've already taken would be sufficient on their own for training the generative adversarial network, but we want to have a bit of fun. We want to output every once in a while a random sample of outputs from our generator just to have a peek at how our generator is improving over time. What do these fake images look like as the model trains? So to do that, we're going to add another modulo here that's less frequent than this reporting modulo here. So we're going to say every 500 epochs, print what epoch we're at, epoch number, we're going to have some kind of log message, some kind of reporting. In fact, this part is so finicky, there's no point in watching me type it out. I'm just going to copy and paste it from the generative adversarial notebook that is available for all you guys in the notebooks directory for these live lessons. There's no point in watching me just type all this stuff out. So the log message stuff is finicky but boring. We're just getting our log messages being printed to screen. We'll see that when we start training. The more interesting part here is that we're going to now just be creating a random 16 samples with the generator. So we're going to sample 16 different random samples of 100-dimensional latent space noise and create 16 fake images. So this is actually the same kind of random noise code as we've used a couple of times now. Except that it's not going to be our batch size. We don't want 128 of these sample images. That would probably be overkill. You can do that if you want, but I only want 16 of them. 16 is more than enough for my eyes. So then those generated images are created by applying the predict method to our generator, with the only inputs being those 16 random noise samples from our latent space, and then we're going to plot out those 16 images. You can assign a figure size of whatever you like. I like 5 by 5 on my screen here. And we're going to plot out, again, this code is really finicky, unnecessary detail for you to watch me type it out and me to explain what I'm doing here. I'm just going to copy and paste from that generative adversarial network notebook. So this is over. We're just outputting a little plot the same way that we output a single sample from our real data set here with this image show function. We're going to do that again here 16 times with fake images. And we're going to specify the layout and show it. And finally, we're going to have this network return to us our overall adversarial network metrics list and discriminator metrics list that we built up over the course of training each of the batches. Cool. Now let's set it going. So our complete A metrics and complete D metrics, we're going to train. You can train for as many epochs as you like at home. You might want to start with 1 or 10 or 1,000, a relatively small number, and then you train this for as long as it takes to get some good looking outputs. So I've already run this notebook. You can pop over to the completed notebook here, and we can see that my after 500 epochs, you get these rough apple shapes. You can see they're a little fuzzy, but those are definitively apples. For whatever category you picked, hopefully you're starting to see some images here as well. If the category that we're looking at is something more complex, like octopuses, you can look at my colleague Grant's notebook here. So he did this same kind of generative adversarial network running on the quick draw octopus category. And because octopuses have so many more intricacies than apples, after 1,000 epochs, you can't really make out what these are at all. After 2,000 epochs, you can start to see some structure in the images being generated. And by 5,000 epochs, yeah, you can see those are probably octopuses. Whereas with our apples, things happen a lot more quickly. So we're seeing some pretty compelling looking apples after 1,000 epochs, a lot of these samples. And certainly by 3,000 epochs, look at those apples. Those are definitely apples. The very last thing that I did here in my code was these lines of code here to output a view at our training loss in the discriminator and the generator over time, as well as our training accuracy in the discriminator and the generator over time. So you can see, for example, that the discriminator, in the beginning, when the generator is creating really poor fake images at the beginning of training, the discriminator has a really easy job telling real from fake. So the discriminator's accuracy is close to 100% at the beginning. But as the forger becomes better at creating fake images, the discriminator has a harder task, and so that accuracy comes down. The generator, in the meanwhile, is also improving its ability to create compelling-looking fakes. The training loss, so the loss that we're trying to minimize, is also, there's this constant fight between the two adversaries to both lower their loss, and so these two things happen at the same time as well. The losses are always trying to minimize, and because the generator is creating more and more compelling fake images, the discriminator loss has this difficulty going down. And so they end up, after about 500 epochs, they kind of meet in this middle point, and we can see that, that's kind of around the point where the apples started to become relatively consistent as well. So most of the learning happened in the first 500 epochs. There you have it. We made it to the end of creating and assessing our generative adversarial network. We started by creating our discriminator, then we created our generator, we tied them together into a whole adversarial network, and we created some pretty compelling looking fake hand-drawn apples. I hope whatever category you guys picked at home looked great too.